So, welcome to the second video of this course on quantum processing. Today, I'm going to formally dig into the details of information theory, or what we say quantum information theory, at some point. And let me tell you first of all that today is considered to be the second quantum revolution. We already encountered the first quantum revolution once we quantize the electromagnetic field into the photon field, and we identify the laser, maybe also the masers, and all the oscillations, the quantized oscillations of the electromagnetic field. But today it's more about information. Today it's more about qubits. So in modern technology today, you hear about the bits. In any computer science, you hear of bits, but let's transform that into another picture, which is the qubit, which is the quantum bit. So what's a quantum bit? First, see here that you can see that the quantum revolution is about the superposition. So the qubits will be the information encoders instead of bits. So what's the qubit? The qubit will be, if we have a wave function like this, psi, it's equivalent to linear combination, superposition of 0 and 1. So the qubit is considered to be both. You have the state 0 and you have the state 1. In quantum mechanics, we write it like a cat operator, maybe a bra, but this vector of 0 can be considered as maybe spin up, as a spin, or as a particle in the excited state. And 1 can be written as a cat operator, as a vector, like this, 0 and 1, and it can be considered as spin down. So this linear combination is governed by the relation that we have amplitude, and this amplitude is the square of those amplitudes is added to 1, which guarantees the normalization of this wave function, of this qubit. And we can extend that further by different strings. If we sum for all subsets like I goes from 0, and then you sum, maybe you have 0, 1, 2, 3, 4, 5. So it depends on this state. Maybe it can be bipartite state, it can be tripartite state, and all of these things. But we have to guarantee that the normalization is achieved. Otherwise, the wave function is in a trouble. So an example of one of the qubits is the plus state. The plus state is superposition and addition. So the addition here is 0 plus 1. And we have the minus state. And the minus state is just, this is what we call the normalization factor. And this is minus 1. So 0 minus 1 is considered to be the minus. 0 plus 1 is the plus. We can have another way to write down such state by the geometrical representation, the trigonometric identities, that you can write cosine 45 degrees. So if you look here at this representation, this is geometrical representation of the cat operators. Here maybe we can have the 0, here we have the 1, okay, and here is the amplitude. If you go to each one's amplitude, you already can square its amplitude and get the probability. So the plus state, if we maybe get here to draw the 0, to draw the 1, this is the plus state, and here is the minus state, the minus 1, and here's the plus 1, cosine theta. So we have to also mention that if I can take the inner product of, they can overlap the wave character here, it has to be 1. This inner product allows us to construct the Hilbert space, and it should be normalized, should have a canonical delta function for this functions, for those operators. So, sorry. So, one thing also I would like to mention here is that we have, like we have uncertainty between the position and momentum, we have also uncertainty in the signs and the bits. And the signs here and in the bits. We cannot have a commutation relation which is equivalent to 0. They cannot be sort of observables together. And this sign and bit is also usual information in quantum information theory, that we cannot get full recovery of the information for both together. So we already here mentioned the inner product state, and the inner product state just overlap. So actually to get the probability for getting the state together in the Hilbert space. But the tensor product state is another state, another multiplication, another process we can expand the Hilbert space with. If you look, for example, and you take the cat operator of plus and you try to tensor product the plus, maybe also the minus, so it can be written like this, and this is what we actually can see in many textbooks in quantum information theory. In the beginning you see this tensor product symbol. This product is sort of expanding the Hilbert space, expanding this vector. So this goes to this complex space, state vector space, and the string of those states, if you have, for example, a number of strings to n, so the number of strings that you can expand the Hilbert space with goes to this power number of strings. The tensor product state is also actually called Kronecker state. So just to be on the same page of definitions. So let's take an example. Here the example of EPR pair. This is called Einstein-Podolsky-Rosen. This is very intense. One of the most famous entangled state. We'll be exposed to entanglement. But let me just write the superposition of plus. Superposition of 2 zeros and 2 ones. Actually, you can write, because we can take the 0 and tensor product with 0, and plus here you have 1 and tensor product with 1, as you can see here, and the relation is going actually to be sort of this. Tensor product means that you take 1 here with those both, and then 1 multiplied by 1 here, 1, 0, 0, 0, 0, and here the same 0, 0, and here 1 with 0, 0, and 1, 1 as well. So you can get an entangled state that looks like this. Let's make sure that's sort of normalized, it's correctly normalized. If you take the EPR pair and you overlap it again to inner product state, you find that's actually half multiplied by half is equal to 1, and this is correctly normalized. So we already been exposed to tensor product state and also the inner product state. We'll be covering what we call the outer product state in the second lecture, but here let us consider another point of view here, which is the measurements. How we can measure the one of the bases, one of the computational bases of a state like plus, for example. So let's take a plus state again and write down a superposition combination of 0 and 1 here. So what if I would like to measure, to stochastically, or just not maybe stochastically, but just combine or collapse this state into one of its configurational bases. So if I would like to measure the 0, so I overlap the wave function with is 0 with the state I would like to measure, and I take the square here. If I do that mathematically, you find exactly it's equivalent to half. And if I take the other vector, it's actually equivalent to half as well. And you can maybe map it quickly. You look at the normalization condition plus beside the 0, and you look also the normalization factor or condition with the 1, and you find that you can square root, you can take the square of the 1 over square root 2, which is equivalent to half-half. So it's 50-50. Here we measure over the same computational basis. What will be the case if I would like to measure in different bases? Let's take an example of a wave function here. So the wave function will be, I put it 1 over square root n to just say that we have different probabilities for 1 and 0. So maybe alpha, maybe beta, okay? And what if I would like to measure this in a different basis rather than 0 or 1? Let's say I would like to measure that in the basis of plus and minus. So I would have the opportunity to take each vector, each cat, to write it like this. There is no objection over this. So just plus minus, which is actually the cat operator. And this is exactly the minus and the plus. So I write down, I take them and transform them to write down in the corresponding basis I would like to measure in. And the same for 1.